All right, so let's get started. The last evening, you heard from Jerry Miller, who's the head of the sustainability programs at the National Academies of Science, Engineering, and the Institutes of Medicine. Remarkable guy. And tonight, you're going to hear from someone who is of equal stature. I've known tonight's speaker for approaching, I think, 40 years. I rank him among the top oceanographers, coastal engineers, coastal processes experts that this nation has ever had. They would include his mentor, Doug Inman, M.P. O'Brien, who many consider to be the father of modern coastal engineering, who was at Berkeley, and then Bob Dean in Florida. And Ron Flick combines a mastery of theory with innovative observations in the field, and he puts those together in ways that we can cope with some of these serious coastal issues that will only grow in severity. Ron reminds me often that once, many years ago, 35 or 40, I had the opportunity to hire him. And it was probably the biggest mistake I made, and he tells me that if I had hired him, I wouldn't be feeding fish today. But he's a good friend, a good colleague, and a remarkable coastal scientist. Born in Germany, grew up in New York City, earned his bachelor's degree at Cooper Union for the advancement of science and the art in New York City, which is a wonderful institution. And then he got his Ph.D. at Scripps Institution of Oceanography. You have his bio in your notes, so I'm not going to go through all of this, but just to thank him for being here. Whenever we have something, a group of people like this, and an important topic, he's always willing to come and speak with us. So let me go through just a few of these slides from Jerry Miller. This is the definition of sustainability that came out of this report, the Brundtland Commission. And I think the definition on page 3 that you have in the handout is a better one because it puts the emphasis on you meet the needs of the present without compromising the Earth's ability to provide the ecosystem services, the life support system needed for future generations. So this one's a little outdated. Sustainability has 3 different components. So it has the environmental component, the social, and the economic, and it is where all 3 intersect that you have sustainability. And Jerry had this slide up with these growing challenges. World population has increased 133% in 50 years. The world per capita energy consumption has gone up 55% in the last 50 years. And I'll let you look at the others. But we've had rapid change in the last 50 years, and we live in a time that is the most dramatic and most rapid change we have ever had. The 4 main principles of urban sustainability: number 1, the planet has limits. Number 2, human and natural systems are tightly intertwined and come together in cities more dramatically than any place else on the planet. And remember, cities have long been cauldrons of creativity. It's where social movements began. It's where the environmental movement began. And principle 3, urban inequality undermines sustainability efforts. And the growing inequality that we see is a real threat to sustainability. And principle 4, cities are highly interconnected. That gives opportunities for conservation of energy, water, all kinds of things that we don't have anyplace else. Urban environments, cities, can be the best friend the environment ever had. And I think I mentioned last week, when I was in graduate school, we used to think that 2-acre zoning was the best thing for the environment. and we were wrong. The best thing is to congregate people in cities and leave more of the land available for nature. This was those spider graphs that nobody could see in the back. This is for the average for the cities of the U.S. And I'm going to step over here so I can see this. So the qualities that are measured are air quality, the percent of people above the poverty level, public safety, ease of getting to work, the financial health, the residential, carbon efficiency, and the existing tree canopy. And this is the average for all the cities in the United States that they studied. And then he put this figure up for those in the back. It was like an eye chart. And the only thing you have it in your handout, so you can look at these. But so you can see that in remember, the larger this is, the more sustainable you are. So the closer you are to the margins of this, the more sustainable. It's not surprising that in Los Angeles, the ease of getting to work, not so good. Public safety was surprisingly good, I thought, for Los Angeles. And I was very surprised that in New York, the ease of getting to work was less good than Los Angeles. And public transportation in New York is so much better than in Los Angeles. But this was what their analysis indicated. Cedar Rapids is a very safe place to live, but who wants to live? Flint, Michigan, near where I grew up, that's the smallest of these, the least sustainable. That's the place that had all the water problems. That's the place where the General Motors was the #1 employer, the jobs left. And so you can look at this and compare some of these cities. Chattanooga was an interesting example that he pointed out. If you've never been to Chattanooga in the last 10 years or so, it's a very interesting example of waterfront revitalization. And much of it was driven by the Tennessee State Aquarium, which is quite a remarkable aquarium. So I'm going to go through only some of the global constraints and codependence. First finding was the sustainable city exists within the larger context of the planet's finite resources. There's no such thing anymore as self-sufficiency. It's a myth. Whether it's a city, country, but so we do exist within these larger contexts. We can be more sustainable. Long Beach, for example, we import probably 70% of our water, at least 60%, through viaducts. 40 to 50% comes from the Sacramento-San Joaquin Delta and 20% from the Colorado. Long Beach would not be sustainable in terms of water without these imports. We have a very good water department. They've done a great job of encouraging us to conserve water. Long Beach is the leader in converting lawns to drought-tolerant vegetation, which reduces the outdoor use of water by about 75%. And we have done more of that than any city in California. And yet, we've converted fewer than 5% of the lawns in the city of Long Beach. So there's lots to be done. Actions in support of sustainability should not be taken at the expense of sustainability of another. That would be very easy to do, but you have to consider the society that you're in, the state you're in, and so make your efforts consistent. Strategies have to be multi-scale. That certainly is demonstrated here in California. You've got to do these at different spatial scales and temporal scales. Urban leaders and planners should integrate sustainability policies and strategies across spatial and administrative, and I would add to that, and time scales. Science-based solutions that are successful locally can provide useful information to other urban areas around the world. And so urban leaders and planners should gather scientific input, and I think that's what most cities do when they start to do one of these efforts. So when we did the one for Long Beach, we looked at what lots of other cities were doing and used that to inform what we did. Key pathways to urban sustainability include institutional and sectorial collaborations. Cities should ensure broad stakeholder engagement. And that broad stakeholder engagement really is important to get buy-in, because on the pathway to urban sustainability, there are sacrifices to be made, and if it doesn't include some bottom-up agreement, they're not going to be very successful. Cities that have developed a cohesive sustainability plan, et cetera, some of their conclusions are so patently obvious, I don't think they're worth repeating. You can read what they are. Reducing inequities promotes sustainability. That, I think, is a very important one. The greater the inequity in cities, the greater the potential for unrest, and the less you're going to get the commitment to move toward sustainability. Sustainability plans and actions should include policies to address social justice. Long Beach is an interesting example. The people who are the greatest risk in Long Beach are the poor, the elderly who live along the 710 corridor, where they have some of the highest asthma rates in all of California. And even though the Port of Long Beach and Los Angeles, they've reduced their emissions by a significant amount, they are still way too high. And so we have to focus on how we can provide them with more social justice in these practices. The pace and scope of the actions don't appear to be sufficient to meet urgent global challenges. And I think our speaker tonight will talk about our efforts to cope with sea level rise and coastal flooding, and that our efforts probably are not anywhere near at the pace to meet the growing demand. Homelessness, this is a big problem. It's a big problem in Southern California. Los Angeles has the largest number of homeless people of any metropolitan area in the country. More than 50,000 people are chronically homeless. That means they've lived on the street for more than a number of years, and I've forgotten what that number is. If you're going to be homeless, being in Southern California is pretty better at this time of the year than being in Boston or New York or Washington or Philadelphia. But we do have to figure this out. In a recent bill passed to help provide money for some of this housing, it's an important step, but certainly not enough. High priority sustainability challenges, connections among energy, food, and water. It's that nexus that is so important. Diverse and healthy ecosystems, that is what the second part of the definition of sustainability means. If you don't maintain those, the others will get you. Enhancing the resilience of communities to extreme events. The ability to bounce back, and as we talked last week, maybe a better way to do this is bounce forward to the new normal that we find ourselves living in. Human health and well-being. Agricultural practices influence nutritional content and contaminant levels in food, and land use decisions affect levels of physical activity. The food crisis is one that's going to grow in intensity. It's hard for us to realize, but the UN says we need 70% more food by 2050. We already devote 70% of all of the fresh water on the earth to growing our food and raising our livestock. And we use 50% of the ice-free land surface for agriculture and for growing our livestock. You can't scale those up because there's not enough land and there's not enough water to increase production by 70% using current agricultural methods. And one of the things we had a long meeting last week about was, if you look at what percentage of that water goes to growing livestock and how much of that 50% of land goes to grazing, it's about a third. And So the group that we had together were nutritionists and food security experts, and they think we need to raise more fish in the ocean. It's a more healthful source of protein for humans to eat, and it's more healthful for the environment because it doesn't take much fresh water except when you process the seafood, and it also has a lower carbon footprint.
You know, 70% more food, but how much percent of the water?
We use you need to grow 70% more food, and today we use 70% of all the available fresh water. And in California, we use 70% of our available water for our agriculture. And we've got the largest agricultural economy in the country, twice number 2, Iowa. Iowa surpassed Texas, and it's about 3 times Texas. But do we really have to grow some of the crops that we grow that are low value and water intensive? Last year, for example, we had 1 million acres in cultivation of alfalfa. For those of you who don't have a rural background, it's hay. Most of that was shipped to China to feed to cattle. Cattle emit a lot of greenhouse gases. It used to be that agriculture was a very important part of this state's gross domestic product. It still is a very important part of our economy. But if you had to make a guess, what fraction of our gross state product comes from agriculture? What do you think it might be? 60%. 60% over here? Who has another number? 40 and 60. 20%. It's actually less than 5%. Less than 5%. Now, we are the major breadbasket for fruits and vegetables for this country, and we don't want to lose that. But I think you could pair off some of those products that takes an awful lot of water. Anyway, so pardon? In California? Worldwide, we use half of the ice-free land surface. And about 1/3 of that goes to raising cattle and other livestock. So these were the Los Angeles metropolitan area, including Long Beach, that got the greatest attention. Water quality and supply, severe drought, air pollution, urban sprawl. And those are the ones that are our factors. Now, sea level rise was on there, but sea level rise in Long Beach really threatens a fairly small portion of the city, a very important part of the city. But in Jerry Miller's summary, it didn't make it onto that list. Poverty remains a significant issue. I've already mentioned that. You can't have a sustainable economy if 22% of the people live at or below the poverty line. And integrating societal issues into sustainability decisions is really important. So now, with that, I have served my function as the warm-up dog act for the main act. And our distinguished speaker is now awake. And so, Ron, come on up. Please join me in welcoming Dr. Reinhard Ron Flick.
It's always a pleasure to be here. I just don't know how to follow this guy. I just don't. Yeah, thanks. So 40 years ago when Jerry and I first met, he turned me down for a job, and I'm going to follow in that tradition and not do what he asked me to do tonight either. And of course, what he didn't mention is that he did both of us the biggest favor of our lives. Me, for example, I got to waste away the last 40 years at Scripps in La Jolla instead of the eastern backwoods of Long Island somewhere. But thanks for that introduction. Thanks for that introduction. The three engineers and scientists that he compared me to, by the way, are all dead. He neglected to compare me to anybody living, right, that might actually be better than I am at this. All right, so with all that comedy, and I'm gonna make like Saturday Night Live for anybody that saw Melissa McCarthy and starts asking nasty questions. So we have a question here before us in this class. Can we make our coastal cities resilient to climate change, or are they doomed? I have a personal opinion, and I'll try to get to that at the end. At the very end, you'll see we'll have time for some chillin' among the warming, and we'll have a beer and maybe time for some philosophy. Do not look ahead in that handout. All right. So I can only talk about what I know. And I know very little about resilience. I don't know the jargon. I don't know the concepts. I do know a little bit about the physics, about how the coast works, especially the California coast. I know a little bit about sea level because I've been studying that since the late 70s, early 80s, when there were about 6 or 8 people that gave a rat's can I say that? Gave a rat's patootie about sea level. And now, of course, everybody and their brother-in-law is studying sea level. So I'm going to talk a little bit about that. So there's an outline. I want to talk briefly about what the greenhouse effect is. For those of you that may not know, very simple explanation. I want to talk about the radiative imbalance, why the Earth is warming. And I want to go to the paleoclimate. I'm going to go back probably 60 million years, and we'll work our way slowly up, to yesterday. Talk again, like I said, about sea level, how flooding, erosion, and damages occur on the California coast, at least. And then a little bit about the California coastal setting to illustrate why it's different. So you'll see that all of this, of the many subjects that we could talk about, of these complicated subjects, complicated and complex, and I'll get into the difference between those a little bit, about what we could be talking about here. These are the things I understand, and so I think as far as they go to helping make a decision about how we can make cities resilient and why they aren't, especially as applied to the California coast, you'll have to put those pieces together. So that's what I'm going to try to do. I'll try to introduce some of these concepts. And then I'm going to try to figure out how to make the slides go forward. Yeah, okay, well, that didn't work. There we go. Okay, forward. There we go. Okay, the greenhouse effect. So the greenhouse effect is a good thing. So, lately in the last 20 years or so, everybody would think that it's a bad thing because it's making the Earth warm. Well, it's a good thing because the Earth is actually 15 degrees centigrade, 27 degrees Fahrenheit, warmer than it would be if it didn't have an atmosphere. So we would be a lot more like the moon. It'd be a lot colder. And not only would it be a lot colder, but it would also be very hot during the day, right, when you're facing the sun, and very, very cold indeed at night. So we just couldn't have the kind of life on Earth that we have without the ocean and without the atmosphere moderating the heat and cool. So what's going on here is we have an atmosphere. There it is. Well, it's a surreal atmosphere. It's not blue, it's green. Okay. So there it is. That's the atmosphere. And we have greenhouse gases in the atmosphere, carbon dioxide being the one that gets all the press, but there are hundreds of others, methane being a very important one, or as Jerry put it, cow farts, right? That's what cow farts are. They're methane, and that's how come they increase greenhouse gases. Of course, natural gas is also methane. So methane is a very important greenhouse gas. It's shorter lived, but it's more intense. It has, per concentration, more intense effect on warming than CO2. The point here of this illustration is that the sun shines, right, and it has visible light that penetrates the atmosphere, hits the surface of the Earth, where it warms the Earth, but not to the heat of the sun, right? So the light that comes into the Earth is visible, but the Earth, if it's under radiation balance, radiative balance, has to give off as much radiation as it absorbs without change, so it doesn't change temperature. So if the Earth's temperature were stable, which it really never is, it always goes up and down to some degree as greenhouse gases build or are taken out of the atmosphere in geological time. And in current time, because we're putting so many greenhouse gases in it. But the point is, in order to achieve radiative balance, the amount of radiation that goes in has to be the same as the radiation going out. So the radiation going out is infrared because the Earth is a lower temperature than the sun. That's why the sun's light coming in is visible, so it can penetrate the atmosphere. The radiation that the Earth gives off is at the average temperature of the Earth, about 60 degrees or so. And so it comes off in infrared frequencies. That part of the atmosphere is opaque, and that's where this idea of a greenhouse comes from. The physics is a little different than an actual greenhouse, but the effect is the same. So in the wintertime, if you have a glass house, the light shines in, and it's nice and cozy warm for exactly the same physics, because the light from the sun can penetrate the glass, but the glass is opaque to the infrared, and it can't get back out. So you can also think of it as a blanket. You have a blanket on, right, at night, so you trap the heat inside. Now, as the blanket gets thicker, as the greenhouse gases build in the atmosphere, that blanket gets thicker, the glass gets a little bit less opaque, and the outgoing radiation is a little bit less than the incoming radiation. Right now, the radiative imbalance is a little bit less than a watt per square meter. Square meter is about this big. Well, we used to have 100-watt or 60-watt light bulbs, so you get a feeling for what the radiative imbalance is. And as this radiative imbalance grows, it's been growing and it's going to continue to grow. I'll show you that in about an hour. The Earth has to warm, right, to try to equilibrate its outgoing radiation with the incoming radiation. Now, this is not a new idea. There was a guy named Svante Arrhenius in Sweden in the 1890s. He won the Nobel Prize in chemistry. He was the grandfather of actually a Scripps professor that's still alive today, Gus Arrhenius. And he did the calculation and he noted in the 1890s that greenhouse gases, CO2, from the Industrial Revolution being spewed into the atmosphere at those rates in the late 19th century had the potential for warming, and his calculations, he was a smart guy, remember, Nobel Prize, were pretty much on the mark for this so-called climate sensitivity, for increasing CO2 and how much temperature rise is associated with that. So this is not a new idea. The physics are well known, well documented. There's no controversy or disagreement about the basic physics of how this works. The timing, there are a lot of uncertainties that we'll get into, but the physics and the fact that this is going on is not a debate. There's no debate about how that works and why it works this way. All right, so here we are. This is the famous Keeling curve, named after Dave Keeling, who was a scientist that Roger Revelle hired in the late 50s in order to start measuring CO2 in the atmosphere that hadn't been routinely measured at the time. So at the time he started making measurements here in 1958 or 9, we were down here about 310 or so parts per million. This is on the quiz, by the way. Jerry didn't tell you it was a quiz? Okay, so remember this. So a couple of weeks ago, late 2016, we broke the 400 part per million mark. So we've had an increase of about 50%. What? Yeah. Feel free to interrupt, by the way. This is a class. I get to talking and I don't stop, so interrupt me if there's something that you need to ask. So where does this last 60 years or so fit into the history? Well, here's a chart of CO2 over the last 800,000 years. So this is about the time Jerry was in grad school. When this time series started. Now you'll see these numbers. You'll see these numbers over the last 800,000 years bounce around between about 190 parts per million and about 270, maybe 300. I'm going to talk a little bit about this period of time here, 125,000 years ago, in a little while. This is the Eemian, where we had 270 or 80 parts per million. And then here we are today. So this is the so-called hockey stick. This is why it's called a hockey stick. It is unprecedented in the history of the Earth to have greenhouse gases increase at this rate. So there's been plenty of times in the past, 600 million years ago, 300 million years ago, where there were many thousands of parts per million, a couple of thousand parts per million. The Earth was much, much warmer. Dinosaurs walked around, big plants growing and all this stuff. But the changes never occurred, of that magnitude, never occurred this fast. So we are in uncharted territory, even though Dave made a chart. Okay. So here we are in pre-industrial times. We were down here where the arrow is, about 270 or so. And now we're close to 400. We are well on our way to a doubling of CO2 over the pre-industrial time. So 270, quiz, 270, doubling, how many is that? Quickly, come on. 540, yes, thank you. Okay, so we're on our way to 540. I'll talk a little bit about the temperature that is associated with. So here we are. This is 1880, when I think Jerry graduated from grad school. He was in there for 800,000 years. I just can't resist. You know, we were talking over dinner about how easy it is to make fun of Jerry, and it's just, he's such a sweet and nice guy and such a smart guy that it's just irresistible. All right, let me get moving here. So this is a chart that has the average over some period here, I don't know, 60 to 90 or whatever it is zero. So this is relative temperature to some average period. And you'll see that the effects of the most recent warming, we'll get into some of the previous ones in a little bit, the most recent warming over the last 100 years or so really started to kick in at the beginning of the 20th century, and the temperature has risen about unevenly, this is global land and ocean together, about 1 degree centigrade, so almost 2 degrees Fahrenheit over the last century. And you'll notice here 2014, 15, and 16 were records, all-time records for the instrumental record, at least over the last couple of hundred years. So remember, what was the Paris Agreement, right? In Paris, they had this agreement. They were going to limit temperature to what? 2 degrees. Yeah, 2 degrees. So we're already halfway there before we even went to Paris, right? All right, so there's all this heat building up from this radiative imbalance. Where is it going? Well, about 90% of that heat, see, the atmosphere gets a lot of play, but about 90% of that heat, oh, I should mention, half of the carbon dioxide that's being put into the atmosphere ends up in the ocean, but 90% of the heat ends up in the ocean. So the ocean heat content, now this is a little bit confusing, so because they've subtracted out the mean, again, over a certain period of time here somewhere, they've subtracted out the mean number of joules. So joules is the metric unit of heat. Can't remember how it relates to watts, but it's got something to do with just, I don't know, think of heat, right? So when you heat up your pot of water on the stove. And so what they're plotting here is the change in the heat of the ocean over the last 60 years or so, since 1955 or so. And the way we've measured this, or measuring it currently, believe it or not, there are almost 4,000 floats out there in the ocean. This project is a huge international effort. There's one of them. They're called Argos floats. And they're deployed and recovered, and they float around out there for a few years at a time. And this was a year, almost a year ago. There were close to 4,000 floats And what they do is they float on the surface to transmit their data, and then they sink down to 2,000 meter depth, right? So 6,000 or 7,000 meters. It's almost half of the average ocean depth. The average ocean depth is about 5,000 meters. And they measure the temperature as they go down and back up again over, I think, a few days or a week that they go up and down. And then they go up and they transmit their data to a satellite, and that ends up somewhere in some data center. And so all of this has been going on for about 10 or 15 years now. And so we have an excellent measurement of the heat content and how it's rising in the ocean. And again, this is measurement. This is not, there's no controversy, no debate about any of this. So what are some of the symptoms of this ocean warming and CO2 going into the ocean? First of all, acidification. Everybody's heard of ocean acidification and all of the bad things that happen. That gets a lot of the press, but it's actually only one consequence. It's a direct consequence of CO2, this half of the CO2 that we're pumping, excess CO2, that we're pumping into the atmosphere ending up in the ocean. So what are some of the symptoms of acidification? Anybody tell me?
Might take out the bottom of the food chain, right?
Yeah, right. Bottom of the food chain, and also oysters, right? So some of the things at higher trophic levels, anything that has a calcium carbonate shell, or anything that's anybody that has a shell out of copper. I don't know. And you put a penny in a Coke bottle, you see what happens with acidification. So this is not to say that the ocean is acidic. The ocean's not turning into hydrochloric acid. The ocean is still basic, right? The pH is higher than 7, but it's coming closer to neutral. It's becoming less basic as time goes on. And that is a big deal. However, these other things that are related to the warming are potentially even more catastrophic. There's a recent paper, if you want to look at it, talking about a deep ocean famine. So in other words, a collapse of the phytoplankton, the planktonic life in the ocean that then will cascade upward and jeopardize everything, fisheries and everything else, leading to potentially huge food shortages. I was going to say I can't remember the other authors, but there's a co-author named Lisa Levin, who's a benthic ecologist at Scripps, and she's a co-author of this. It's a fantastic paper. If you want to think about sustainability and the consequences of warming, this thing will really, you shouldn't read it before you go to bed. So fisheries collapse, decreased organic material, so the fertilizer in the ocean is going to decrease primary productivity. I already said that. Phytoplankton, like other plants in the ocean, like land-based plants, turn carbon dioxide and water into oxygen. Well, we need oxygen, right? We want to breathe. And this is actually a funny story. So I mentioned Dave Keeling, who started the Keeling curve, right? These CO2 measurements made all over the world now, but started in Hawaii. His son is now, Ralph Keeling, is now a professor at Scripps. He decided to do his Ph.D. thesis, because it's quite a while now. Ralph is getting in his 40s, I guess. And I don't know if it was a spiteful, sort of, oh, my dad's doing CO2, and CO2's going up, so CO2 takes carbon and oxygen, so therefore the oxygen must be going down, right? Logical. So he did his PhD thesis, and he's still measuring. There is a measurable decrease in atmospheric oxygen, right? Because some of it's being converted to CO2 through this oxidation process. So this is a sort of an interesting personal anecdote. I can see everybody's falling asleep. Okay, great. All right, so some of the physical changes that have been looked at: increased storminess. As the ocean surface warms, more of the energy is going to be available into the atmosphere to make storms, right? Because the gradients are going to be bigger, the differences in temperature, and there'll just be more heat as the heat engine to drive these storms. Now, interestingly, a couple of us collaborated in a paper. The lead author is a guy named Peter Bromirsky. If you want to read about this, it's really interesting because we looked at all of the tide gauges along the west coast of the U.S. And you should be able to see increases in storminess in the storm surge, but we can't find it. It's not there yet. So, and this we had a co-author that was a modeler, and he was like, no, my model says that storminess is increasing, and we're going, sorry, Art, but the data says it's not. So he went back to look at his model, and so we're going back and forth about this. But this, it brings up this question about how do these ocean models work? How can you rely on them? What do they tell you? You have to go back to the data, right? We have data. We have 100 years of tide gauge data, and so we looked at all that. And the storminess is not really hasn't really shown up yet. In the future, this is a really scary thing. When I say profound circulation changes, because of the warming and because of fresh water from melting of ice caps, that especially in the higher latitudes off Antarctica and up in the Arctic off of Greenland and Iceland, all of this fresh water that's going to be or is now increasingly floating around in the surface of the ocean is making the stratification bigger, so you're not having sinking of deep water. Atlantic deep water formation. And that whole, if that process collapses, the Gulf Stream goes away or weakens considerably. If the Gulf Stream weakens or goes away, then even as the rest of the world is warming, Northern Europe will go into a deep freeze because it's the Gulf Stream, it's that warm water being transported up along the east coast of the US and across the North Atlantic that keeps Ireland and the Scandinavian countries at a more or less moderated temperature that would disappear if that circulation of the North Atlantic shuts down, which it could. It has in the past. Paleo data show that the Gulf Stream has turned on and off over time, and so that could happen again with very serious consequences. Is that better when I talk like that? That's a really good question, and we'll get into timelines. So I don't know, but it's it's not 800,000 years, right? And it's not a million years. It's decades to century. It's on that time scale. Now it doesn't mean next week, and it might not be in 20 years, but it could be in the next 100 or so. Hope that helps. Where were we? Okay. So now this is interesting, but a little bit complicated. Can you see this? Okay. So this has 3 or 4 different time scales, and I want to give you a little bit of a geological perspective, and I want you to remember these numbers in the context of the warming that we're talking about. So this scale from here to here is 500 million years. Well, okay, 400 million. And then from here to here is about 60 million, from there to there. So 400 million, real long. 60 million from here to here. 1,000 years, thousands of years, so 1 million years from here, and then 20,000 years from here to here. Does that make any sense? So this is a compressed and then greatly expanded time scale. As we look at temperature. So this is from temperature relative to 1960 to 90 average is here. So the Earth was as much as, in the last 500 million years, 14 degrees, and this is centigrade, so almost twice that, 25 degrees Fahrenheit or so, warmer than it is now, considerably warmer. Much higher CO2 concentrations, as I said. And there's been a cooling, about a 60 million year cooling trend. 60 million year cooling trend that we see starting here in the Eocene, all the way through the Pleistocene, the last 5 million years, Pliocene, and then the Pleistocene, this last million years or so, into the last 20,000. So over this period of time, about 30 million years ago, is the last time the Earth was ice-free. So this is the last time that there was no ice at the polar caps or on the continents. There was no ice. It was too warm for ice to form essentially anywhere. So I would say, well, there was grass and cows were roaming around Antarctica. I don't know about the cows, but there was probably grass. Okay, so 30 million years ago, the Earth, and people think that this has to do with the shifting of the plates, the plate tectonics, either turn off or turn on carbon dioxide sources that then gets into the atmosphere with feedbacks over many centuries and millennia, then lead to these large changes in temperature. So 30 million years ago, we went into this long cooling cycle where the Earth cooled probably 8 or 10 degrees, right, from a +6 down here to the -4 relative to the 60 to 90 average, okay, 1960 to 1990 average. Think about that. Let that sink in for a minute. So over 30 million years, the Earth cooled 8 degrees. 8 degrees. We're only talking about 8 degrees, right, between an ice-free Earth and the Earth we have now. So once the Earth became cool enough to sustain ice, we went into these, and this is driven by solar cycles, we went into these many hundreds and thousands of 100,000 year, 20,000 year, 40,000 year long ice ages. So the comings and goings of the glaciers. Culminating in the last one, I want to talk about the Eemian in a minute, culminating in the last one 20,000 years ago when it was 4 or 5 or 6 degrees colder than it is now. Only 6 degrees, 11 degrees Fahrenheit, 6 degrees centigrade colder than it is now, but sea level was 400 feet lower. Think about that. 6 degrees centigrade, 125 meters. Do that in your head. That's 21 meters per degree centigrade. 21 meters per degree centigrade. How much has it warmed in the last 100 years since 1880? Anybody? 1 degree. It's warmed 1 degree since the Industrial Revolution started, right? And we went to Paris and said we're going to limit it to 2 degrees. 1 degree, okay, round off. That's 21 meters. 21 meters of sea level is probably already baked in. Probably already baked in with the warming that's already here. All right. The Eemian. So what do we know about the Eemian? We know this for pretty sure. It's only 125,000 years ago. As I said, Jerry was in school. He was making these observations. 120,000 years ago, it was about 3 degrees warmer, and sea level was 6 to 9 meters higher. So what does that mean for us? Yeah.
Question. It seems pretty clear that there's a direct correlation between CO2, temperature, and sea level rise. Is it always correlated, or sometimes are they out of whack with each other?
Well, sometimes they're out of whack because it's a complicated thing. And one of the problems that I had, and I know that climate change deniers have brought up over and over, there are some periods, a few periods in the geological record where the temperature goes up and then the CO2 follows, right? So a question of lead, lag, cause, and effect, right? So, well, wait a minute, so we're going to put, so CO2, so sometimes the temperature goes up and then the CO2 follows. Well, they're inextricably connected. If one goes up for whatever reason, the other one's going to go up as well and down. So perfect, no. What's the climate sensitivity? Depends, this is a very complicated as well as complex problem. So let me give you a brief introduction to the difference between complicated and complex. You're going to ask that. Okay, so complicated. Jerry mentioned the water system in California. That's a complicated system. So think about, so complicated essentially means a lot of moving parts, a lot of pieces, connected in very complicated ways. However, it's predictable. You put water in one end, You pump it around lakes, reservoirs. It falls as rain and snow. It ends up in the rivers. It goes into reservoirs. You pump it out of reservoirs. You put it in the filtration plant. Then you pump it in, and you turn on a faucet somewhere, and water comes out. If you put less water in, less water comes out. It doesn't have, if a pipe breaks somewhere, it floods a block, but it doesn't screw up the whole downtown, or it doesn't screw up Los Angeles if a pipe breaks in Long Beach. Okay. Now think of the electrical system. Electrical system is very similar, right? You put electrons in one end, that's like the water. Instead of pipes, you have wires. Instead of faucets, you have switches. Okay, but it also has an element of complexity. And complexity has elements of not quite linear. So very small changes can make very big effects. And we saw this in these blackouts, right? We've had blackouts where a transformer explodes, somewhere in some suburb somewhere, and the lights go out in Chicago. Why is that? Because it cascades in some unpredictable ways. These are very complex, not just complicated systems, but complex systems. The climate system, it's almost like your brain, right? Your brain is a complex system. Some people get shot in the head and they're fine because of these complex that we don't understand interconnections in your brain. This part got shot, no problem. I'll just move that stuff that I did I'll move that over here. And that's unpredictable, it's nonlinear. Most people, they just die when they get shot in the head. But it's complex because you can't predict the outcome. Very small changes can make very big effects. The climate system is both complicated and complex. And that's because of the feedbacks. So I'll give you an example of a feedback. So these ice ages are paced. The pacing is driven by very small changes in the inclination and the orbit, the eccentricity of the orbit around the sun. And those occur at about 20,000, 40,000, and 100,000 year timescales. They're astronomy. It's highly predictable. But the effect is very, very small. You're talking about a tiny, tiny little bit of change over 20,000 years of the amount of sun, right, that reaches the polar areas. But that's just enough to make, on the downward cycle, on the cooling cycle, say, just a little bit more ice, freezing and snow in the wintertime. And then that's a white surface. So now that reflects a little bit more sunlight than it did the year before, or the millennium before. And so that's a positive feedback. So it reflects a little bit more light, so it gets a little colder, so you get a little more snow. That reflects a little bit more light, and so you get a little bit colder, and reflects a little more. So you see what happens here. It has a positive feedback to get colder. And then, 20,000 years later, you end up with a mile of ice over New York, which is what we had here. 20,000 years ago, there was a mile of ice over Central Park. The glacier, the Laurentide Glacier, ended up in the middle of Long Island, right where Jerry's University was out there at Stony Brook, right? And over Central Park, you can see the scars in the rocks there. So very, very small changes in the light lead to these nonlinear cascading feedback effects, and that's just one of them. And CO2 is another one. And now we're on the opposite trail. So a little bit of warming kicks up a little more CO2. It kicks a little bit of methane out of the tundra, for example, or out of the continental shelf where all of these frozen methane deposits are, and it gets a little bit more greenhouse gas. It warms up a little bit, and that kicks a little more methane up. So quite apart from this super interglacial that we're in now, quite apart from that, these natural fluctuations are highly complex and highly nonlinear because very small changes can make very big effects. All right, let's get moving here. So, didn't we do that already? Looks familiar. So this is the last 20,000 years. So this is one more point I want to make. Again, 6 degrees and 125 meters of sea level. So this 20,000 years ago, mile of ice over New York, all of that melted. And so we have the ice conditions that we have today, more or less, starting 8 or 10,000 years ago. Well, 8 or 10,000 years ago, what happened? Well, agriculture started about 10,000 years ago. Coastal civilization. You think about the Egyptians are around here somewhere 5,000 years ago, the Mesopotamians. Culture as we know it, civilization as we know it, started around here. during relative stillstand of sea level. Sea level didn't go up much. Doug Inman, my mentor that Jerry mentioned earlier, did a bunch of research on this kind of thing. His wife said, you need a hobby. So he said, okay, I'll study ancient harbors and marine archaeology. It's like, no, I meant stamp collecting or something, you know, not something that's going to be all work again. Anyway, he did a bunch of studies. There's a harbor in Israel called Caesarea. Guess who built it, right? Caesar, around the time of Christ. You know, and the docks, you know, in the 60s when Doug was doing his research, were only about this much underwater. All right, so for 2,000 years, there was only a little bit of sea level rise, right? Until about the, I don't know, 1880s or so, when, you know, sea level started to really accelerate, as I'll show you in a minute. The point I want to make here is that this increase in sea level, so now we're talking about sea level associated with this 6-degree change, right, from 20,000 years ago. This didn't go smoothly because, well, why? Because of this complexity. And so in this case, we had these examples. This is the big one, right? It's called Meltwater Pulse 1A. Okay, meltwater pulse. So the sea level rise was 3 to 6 meters per 100 years, 30 millimeters a year, 3 to 6 meters per 100 years for 400 or 500 years. Now go look outside. Well, it's dark now, but you know that the water levels may be what, 4 or 5 meters below that pier deck over here. So think about this. So the current rate of sea level rise, anybody know what it is in the 20th century, more or less? How many millimeters a year? It's easier to talk in millimeters in this case. About 2 millimeters a year. An eighth of an inch is 3 millimeters, just in round numbers. Since the 90s, it's increased. It's about 3 millimeters a year now. This is 30 to 60 millimeters a year, right? It's 10 to 20 times higher than what we have now for 400 or 500 years. And why is that? Well, they think it's the Laurentide ice sheet, this ice sheet that covered North America, just suddenly collapsed. Suddenly, you know, in geological time, over a period of a few hundred years, this thing collapsed. So the same thing could happen in Greenland, the same thing could happen in West Antarctica, or even East Antarctica, God help us. And then we have, anybody know how much sea level is still tied up in the ice? Roughly? A little more. There's about 6 or 7 in West Antarctica, I don't know, 2 or 3 or 5 in Greenland, and then about 60 in East Antarctica. Meters, 220 feet more or less, 230 feet. Additional to go if all the ice melts. So if we go back to conditions we had 30 million years ago, we've got 220 feet of sea level. So there's sea level as you can see it. So think about where that might be. All right, questions? So sometimes people ask me, oh my God, we're only at slide 9, Jesus. People ask me, well, how do you know sea level's going up? It's like, well, San Francisco, somebody went out in 1855 and they went to a pier piling and they nailed a yardstick and they started making readings. They measure it. That's how we know. Yeah. Sure. Yeah, but yeah, but that's evaporation. I mean, yeah, that's a cycle though, right? That water's got to come out. It's not going to hang up there forever. So even if it did, and that's a very small, the freshwater part of fraction of, you know, the amount of fresh water in the Earth's system compared to the amount of seawater it's not even a drop in the bucket. It's like a molecule in a bucket. So no, that doesn't, over very, very long periods of time, as the oceans formed, you know, they started forming, I think very close to where at least the water started coming out of the Earth's crust. I'm not sure this is right, but very close to when the Earth was formed 5-6 billion years ago or so. There's been water on the surface of the Earth for a long time. And so over those kind of timescales, the growth of the ocean, you know, is important. But not on the scales that we're talking about here of, you know, certainly not tens of thousands of years and certainly not over, you know, 150 years. So there's a few things I want to say here. First of all, So this is the 20th century. That's the 2 millimeters a year, 20 centimeters or so in the 20th century. This is in feet, but okay. There was a still stand from the time the record started in 1850 to about 1900, and this is typical because this has to do with large-scale changes of wind circulation, winds in the Pacific. So then we had this increase over the 20th century. Everybody quotes 2 millimeters a year, more or less. And then there was another still stand from about depending where you are, in Southern California, it was 1980 to 2000. Here it's about 1980 to 2005 or so, 10. So looking at the minima, you know, there's a still stand of sea level here, and that had to do with cooling, these cooling and changes in the circulation driven by the winds. And then finally, once that stopped, about 2005 or so, see now we're on this is actually 10 millimeters a year. And this variation of sea level rise, it varies over space. So over the last 30 years, places like Guam have been going up at a centimeter a year. Instead of 2 or 3 millimeters a year, it's 10 millimeters a year. Whereas the Eastern Pacific, our part of the Pacific, hasn't been rising as fast. And now that's shifting. So it's like a seesaw. It's shifting. We're going up faster. They're going up slower. And then finally, the other thing you see here is the effect of the El Ninos. You see, so in 41, 58, 59, 83, this was a big one, 83. 97, 98 was bigger in the south. We didn't see it so much. 2015 El Nino. So you see these big spikes. So you see here in 83, I mean, that's like 100 years worth of sea level for a year or two at a time, right? 100 years worth of sea level rise for a year or two at a time. And that's what people have said, and it's useful in that sense because it can give you a preview of what mean sea level can look like as time goes on in the future. And I'll get to the projections here in another hour or two. All right, here we go with projections. Damn it.
So when they take the
There we go.
sea level, the tide gauges,
Yes.
how do you know how much to compensate? Like, I'm told that Palos Verdes is going up at
Yeah.
an inch a year.
Yeah, I'm going to get to that in a minute. I'm going to get to the tectonic stuff in a minute. But that was very difficult to do before GPS.
Yeah.
So with GPS, that's actually pretty simple. Again, it's complicated, but relatively simple to what it was when you had to do, rod and level surveying. Yeah. So there's a huge network of fixed GPS gauges in California that were mainly put out to look at the strain, right? The changes in the movement of the crust due to the faults, right? The fault movements. But if you leave those things there long enough and anchor them well enough, then you also get the vertical. So now there are GPS stations tied to all of the tide gauges, so you can compensate for that. So it turns out San Francisco and La Jolla don't move much. They move a little bit, but not enough, compared to the change in sea level. So they're pretty good at reflecting what's going on at the sea level part only. LA not so much. If you look at the trend in LA, so the Los Angeles tide gauge, it's right out here in the harbor somewhere. The trend in Los Angeles is quite a bit lower because something must be rising, right? The land must be rising there relative to the sea. You look in Louisiana or Florida, well, in many places in the south, where the land is sinking and sea level's going up at 3 or 4 times the rate. Jerry.
I think at 8:15, let's take a break. And when we
Okay.
come back,
Okay.
my concern is, my calculation is the sea level will rise by about 20 meters by the time you get done.
See, this is why I didn't go to work for him. All right, so you want to talk about Woody Allen first, or you want to take a break? Okay, so this is a quote from Woody Allen's Cabaret Act in the 60s. When you think about this, in 1962 or 3, this must have just been funny as hell. Right? This is when, like I said, when I started studying sea level, there were like 6 people in the whole world that cared about sea level. And as a comedy routine, I mean, what could be more trivial and less noteworthy than worrying about the fear of sea level. And it was like, saying, remember the Timbuktu, and, let's talk about getting lost somewhere, someplace never heard of, like Afghanistan, right, in the 60s. Somebody grew up in the 60s, we're talking about places like Timbuktu and Afghanistan. Well, there's two things people now know. One is sea level, and the other one's Afghanistan. So I'll leave you with that for the break.
Let's take a short break, 10 minutes, and then let's come back.
Okay, so I promise to try to speed this up a little bit. We all want to get home somewhere tonight. So this was an idea that I had that we fleshed out in a paper that you can read. It's online. It's in the Transactions of the American Geophysical Union. And somebody said it was the only paper he'd ever written that has references to both the Bible and the Quran. Well, because they both have flooding stories. So the question is, how do you distinguish between flooding and inundation? As Jerry might have intimated, my first language is not English. And so, in fact, I had to learn English twice. Long story. So I'm a little bit of a stickler for terminology and stuff like that. And it just seems to me that we should stop using flooding and inundation interchangeably. We should use flooding in the biblical sense. If it's wet for less than 40 days and 40 nights, which incidentally, after Katrina, it took 40 days and presumably nights to pump out New Orleans. It's really interesting. Just a coincidence. Maybe. So the tide, right? The tide is flooding. That's periodic, regular period flooding. Episodic flooding is, flooding when you have a storm, or in a river, you have flooding in a river. Inundation should be the permanent situation. So as sea level rise accelerates, inundation is going to become a more important, according, if you use this definition, it's going to become a process in itself, and that's why it's useful to distinguish. So that's my contribution to the English language. God damn it. I was going to say, besides the quote here from this really funny, so there's an important thing here. When we talk about sea level, we think of mean sea level, and processes that associated with the mean sea level, in other words, averages over a long time, are this ice melting and freezing, like we talked about already, ocean warming and cooling, so warmer ocean takes more water, takes more space, cooling less space, and then the relative motion, right, the land motion. So relative mean sea level is, we think of these things which are long-term affairs. The fluctuations around the mean sea level are associated with these and other processes. So tsunamis, wave run-up on the beach, for example, the tides, there's periodic up and down of the tides, storm surges, which can reach, in Hurricane Sandy, reach 26 feet or so, and then these El Nino, La Nina effects where sea level is higher and lower for a year or two at a time, like we saw. So which was it? Was it this one? God darn it. Why can't I get this right? Okay. So what causes flooding and erosion and damages on our coast? It's not mean sea level rise, right? Mean sea level, we talk about mean sea level. We've talked it to death tonight almost. But that's not what actually damages the coast. What actually damages the coast is when you have very big waves that if they co-occur with high tides and enhanced sea level from these other effects like the El Ninos that I talked about, that's when you get flooding and damage. So this was the Martin Luther King Day storm in 1988. Moderate tide, but huge, huge waves. They destroyed Redondo Beach and the Portofino Inn. You might remember this. There were pickup trucks floating upside down in the boat slips. I mean, it was just hilarious. I mean, it was just devastating. If you're a coastal oceanographer, these things are really good for business, right? Because all of a sudden everybody's interested in coastal oceanography. So here's a picture of Ocean Beach in San Francisco, and you can see the huge wave run-up. The wave run-up, see, these are 5 or 6 foot people. See, and the wave run-up can be 6, 8 feet. It can be the same height as the offshore wave heights. So if there's 10-foot breaking waves, the run-up, vertical elevation of the run-up on the beach can be a large fraction of that 8 or 10-foot run-up. Oh, I got it right. Wow. Okay, so going forward, the same thing as sea level rise goes up, the same processes are going to be causing the coastal flooding, coastal erosion, and coastal damages. So when we talk about resilience or being able to recover from damages, well, what kind of damages are we talking about? We're talking about on the California coast. Now, this is the West Coast. We're talking about wave damage, wave flooding, and wave erosion. So those are the important processes. As sea level rise, as sea level goes up, and as it goes up faster, these same processes are going to become more and more acute, more and more intense, and more frequent. So and here's kind of how this worked in 82, 83. So this is December. This is the water level, the whole sea level, the tide. So 30 centimeters, that's about a foot. So the tide range is about 10 feet. In January of 83, so it's December 82, January 83, we had the highest tides in about 18 years, an 18 or 19-year solar cycle. And you'll notice, so this is the storm surge, about a foot, half a foot of storm surge and about a half a foot of El Nino. And then we had 3-meter high waves that coincided, but look at the timing. They're right at the neap tides. You got to invite me back sometime to give my tide lecture because I can talk about 10 or 12 hours on the tides. Really interesting stuff. Very, very fascinating tide regime that we have on this coast. But look at the damage. So there was some damage, but because these storm episodes, the 2 episodes in December, coincided with the neap tides, it just kind of softened the coast up a little bit. Now, in January, we had a long series of storms over a couple of weeks that happened to coincide with this spring tide period in January. And then the haymaker of all on the 27th or 29th, I can't remember, 29th of January, 1983. And that's when $100 million of damage essentially was done in a few days. Very large waves, 4-meter high waves. This is in the south, higher in the north, coinciding with a foot, foot and a half of storm surge plus El Nino, right? This mean level here was raised by a half a foot or so, as we saw in the San Francisco tide picture. And then that coincided with this high episode of tides. So it's very important to remember as we talk about, do all of this jabbering about CO2 and warming and sea level rise, those aren't the processes that cause coastal erosion damage and flooding, right? It's the waves, and it will always be the waves that cause coastal erosion damage and flooding and make, coastal problems, but they will get more severe and more frequent as sea level rise brings those waves up higher and higher. And these are some of the consequences of that. Mission Beach, 2010, a weak El Nino, fairly strong winter. Mission Beach flooding. Huntington Beach lost part of the pier out here. And there's papers about this. You see some of my first papers with Dan Cahan back now over almost 35 years ago. Time flies when you're having fun. Now, urban flood modeling, I want to talk a little bit about this. This is a slide prepared on the thesis work of Timu Galin, who was my postdoc for a while, Bob Guza, my postdoc. She's now a professor, one of my pride and joy. She's a professor at UCLA now. And she is the only one so far, at least on the West Coast, that has on a broad scale done correct hydrodynamically, full hydrodynamically correct flood modeling. And for one thing, an important aspect of this is Newport. She did her thesis at Irvine. This is Newport Beach. So an important aspect of that is you got to get the elevations right. You have to get the elevations of the seawall, the fence structures, to within a few centimeters, because a few centimeters matter in what gets flooded and what stays dry. She found things like floodwaters flowing down a street. If a garden gate was open, that house and the ones connected to it flooded. If the garden gate was closed or had a sandbag in front of it because you have warning, then that area didn't flood. Now things like that are not. So there's a cottage industry of these coastal flood viewers. I don't want to mention a lot of names, but one of them might be NOAA. Another one might be the USGS. Everybody and their brother-in-law has a coastal flood viewer. So this is in a paper, and this is a different Schubert. Oh, it's a Schubert, not a Schubel. Anyway, different guy. Anyway, Timu has written a bunch of these papers now about coastal flooding and how these models actually work. So these things are called bathtub models. I call them, first grader with a crayon model. Because essentially what this is, so let's say you had 7.3 feet of total water level. So you look at a contour map, or you have a map with contours, or a GIS thing or whatever, right? And if you're a first grader and you can color within the 7.3 foot contour, if you color everything red that's lower than 7.3 feet, now you have a flood model. Well, that's ridiculous. First of all, the flooding doesn't all occur at once. The tide is only high for a few hours. There's drainage, there's defenses, there's all kinds of physics that have to be taken in. And if you take it into account, so this is the same identical maximum water level. Here's the bathtub model, prediction of what's going to flood, right? All of what's the name of that island? Balboa Island, maybe? And here's what actually floods. And this is ground truth, right? Because she went out there with the city people during her thesis work. So, if you're going to plan for flooding, this is going to make the city manager run away if he has to plan for this kind of flooding every time the tide hits 7.3 feet. This is, at least for the time being, for the next few decades, this is kind of manageable, right? If you have this kind of flooding, even once a year, you can manage that. This, you wouldn't know what to do. You'd scream and run away, right? So,
The difference that somebody did some planning?
well, what?
Isn't the difference between the two that somebody did some planning?
No, this is just a different calculation on exactly the same thing. This is just doing the modeling correctly, and this is doing the modeling with the first grader coloring everything red that's less than 7.3 feet, whether it's connected to the ocean or not. That's the other thing. A lot of this real estate you can't get to from here. So how's the water going to get there? So you take all that into account, you have much less apparent flooding. Now, that's not to say that we have nothing to worry about, obviously. As sea level reaches, 2-3 meters above current levels, which could happen in the next 100 years, and will certainly happen, over the next 200 to 500 for sure. We're going to have problems, but we're okay for the next few decades, right? There's no reason to panic with these viewer models over the next several decades. Okay, there's fools here. This is Doug Inman. He's not a fool, but there's Doug Inman standing there. This is in Santa Barbara in 1980, and we're looking into the future, which presumably is warmer. So we're here, right? We've already said that temperature's gone up almost a degree from pre-industrial times. The Paris Accords takes us to 2. These are different scenarios for future warming that you can find on the IPCC place. So I want to talk a little bit about the projections of sea level rise. In California, we're lucky if you're a developer in that sense, because you can't ignore the Coastal Commission even if you wanted to. And so the Coastal Commission in 2015, based on a National Academy study done in 2012, published a huge volume. It's on the web, you can find it, sea level rise projections. So they will tell you what sea level rise scenarios to consider. So they had 3 of them in there in the 2015 reports, a year and a half old. They had 3 scenarios, a lower one, a middle one, and a high one, and I've written them down here in feet. So they're 1.5 feet, this is all by 2100, compared to 2000. So relative to 2000, 1.5 feet, 3 feet, 5.5 feet. And you should consider those. Now, in the last few months, work is underway for the 4th climate assessment. California does a climate assessment every 4 years, or whatever it is, 2 years, I don't know. Anyway, somebody's doing the revised climate assessment, and this 1.5 feet, nobody thinks that sea level will only rise by 1.5 feet by 2100. It's going to be higher than that. This, we don't even want to consider this anymore. They're talking about, up here in 9-foot range territory now, 3 meters or so, depending on what you're looking at. So at San Onofre, for example, I think I can say this, I'm doing some consulting work for San Onofre, or we are, some of us are, we're considering sea level rise out to 2150 because they have a long horizon for the deconstruction of San Onofre. So that, that's out. So we're talking about higher rates already.
I think it's a dog.
This guy, I don't know. I think it's Casper or something. I don't know. But so, nobody considers this lower one anymore. So the question is how high this is going to go in the next assessment that's going to come out early next year. So these are the observed, so these are the monthly observed mean sea levels in San Diego. And you can't really see, you can't tell what trajectory we're going to be on. It's going to be another 10 or 20, at least 10 years, maybe 20, until we get out here to 2030 or so, to where the data, because the monthly data and the annual data too, to some extent, have variability from year to year. It's going to be a while. It'll be a few more decades until we know which trajectory we're actually on. So that's one of the problems with making these projections. If I had time, I could get into the uncertainties and where these uncertainties come from. But let me just summarize by saying there's two major sources for the uncertainty in this large spread in where sea level might go in the next 100 years or 200 years. The first one is human, right? And this is a complex problem. We don't know what humans will do to mitigate the effects, right? We don't know what we're going to do about greenhouse gases in the next 20 or 30 or 40 years when it's going to matter what these trajectories are. So that's basically, what did Rumsfeld call it, a known unknown, right? And then the second thing has to do with, again, with the complexity, and that is very small changes, very small differences in CO2 or other factors can make very large differences in what happens and when we reach tipping points to where we get to these melt pulses when big pieces of ice start to collapse and slide into the ocean, land-bound ice. Floating ice doesn't matter. So if the whole North Pole ice cap melts, it doesn't matter, it's already floating. That sea level component is already in there. But it's the land-bound ice masses, Greenland, West Antarctica, and East Antarctica mainly. When those start to let go and flow into the ocean, that's when sea level can jump up by many feet in 100 years. And that's the biggest physical uncertainty is what the hell the ice is going to do. Okay, so this is a little bit different now. So this one was the mean sea level. And this one is the maximum observed sea level. Maximum observed monthly sea level from 1906 when the tide gauge was installed in San Diego Bay. And you'll see that for that middle scenario, so for the black scenario, this one, the 3-foot scenario, I've drawn these curves on here that are the return periods for these sea levels. So once per month, the sea level is higher than this line. Well, yeah, that makes sense, right? So these are monthly, so each of these is at or above that line. So sea level is at or higher than this level, and I've just projected, that's the measurement, and these are the projections using that 3-foot projection into the future. This is the line where, on average, the monthly sea levels are higher once per year, higher once in 10 years, and higher once in 100 years. So you see the 83. So this is the 100-year return line. The height, 5.2 feet, is the 100-year return line that NOAA gives on its website from the San Diego tide gauge. And you'll see that corresponds to 1983. So now you see what sea level does. Now we call this return period creep. So this is the creeping lower and lower of the return period of a given elevation. So here's the 100-year elevation. So by 2000, so this was, I don't know what that was, 2014, I think. So by 2018, this 100-year elevation is going to occur every 10 years on average. Got that? By 2048, right, when I'll be 100 and Jerry will be 200, by 2048, this what's now a 100-year return will occur every year. And then by 2083, right, if we follow this trajectory, every month is going to be what's now a 100-year return. So this illustrates with sea level. Now we have to add the waves on top of that. Right? I don't have a chart. This is too complicated already. But you have to add the waves on top of that. The tides are already in here. So the peak high tides, the storm surge, the El Nino, all of the stuff that the tide gauge measures in sea level, the sea level rise itself, right? You can see it there. That's the sea level rise over the last 100 years or so, is already in here. So that's what this return period is based on, these monthly maximum data. So you can see how fast these, this sea level rise that's projected, that's the medium, that's now the low, right? Was the medium, is now the low projection that the Coastal Commission wants you to consider. the 3 feet by 2100 projection, and how fast that changes these return periods, and how much more frequently these given elevations of sea level will occur. I'm probably going to skip over a lot of this. I wanted to talk a little bit about the setting of the coast and why our coast looks the way it does. It's relatively steep, and that's because we are on the edge between, the border between the Pacific plate that's floating around out here and the North America plate that has relative motion relative to each other along the San Andreas Fault system. I love PowerPoint. So the tectonic uplift and let me do that again. The tectonic uplift, the slow tectonic uplift, and those rapid changes in sea level that we talked about, right? Those 400-foot, those hundreds of sea level ups and downs that have occurred have shaped this coast over the last 20 million years or so in round numbers, 5 to 20 million years, to make it look the way it does. What was I going to say here? So this isn't Jerry's fault. This is San Andreas Fault. And the San Andreas Fault system is not just one fault, right? There it is, the main trace. But it's actually the width of California, right? Here's Nevada. This is the width of California, this fault system, and another width of California offshore. And so this relative motion, it's called right lateral, which always, I don't understand how this works. Maybe you do. So if you're standing here and you look at that, it's moving to the right. You stand over here and you look at that, it's moving to the right. How's that possible? Anyway, there it is. It's called right lateral. And this grinding past each other will put San Diego into the Bay Area in the next, 50 million years or so? It's moving a few inches a year or something on average. Okay, so that's this tectonic setting. And it was a great paper in the last slide if you want to read about it, right there, Inman and Nordstrom. Tectonic classification of coasts, classic. That's basically why the coastal setting here, when you're in New York, it's California is a beautiful coast, and in the 60s it was very uplifting. Well, it is, literally. So what does that mean? Well, for our beaches, that means we have sea cliffs, generally. Most of the California coast is backed by sea cliffs. It has a relatively narrow, flat wave-cut terrace, and that wave-cut terrace was cut by waves over the still stand of sea level starting about 8,000 or 10,000 years ago, right? Remember, sea level kind of from the last glaciation stopped more or less, or slowed way down over the last 6,000 or 8,000 years, and so the waves had a chance to cut that platform, which is now covered with a relatively thin veneer of sand that's easily eroded in a big storm. So the bottom line here, and this is another very important point as far as what the future of the coast, and how the coast works, that the California coast is eroding regardless of what sea level does. Even if sea level were to slowly drop, it would still be eroding. Why? What erodes the coast? Waves, right, waves. Waves that occur during high tides and big storms and elevated sea levels from other things like El Nino. And so the California coast is eroding whether or not sea level goes up or not. And, but the acceleration of sea level will make this process faster, right, and more problematical. So, I have quotes from other people, so I had my own quote. The future is going to be hard enough. Why do you want to do this? So we did some consulting work for the SEAL teams, right? This is the Naval Amphibious Base in Coronado. And I'll tell you what, and I'm not talking about the SEALs like Jerry has out here. I'm talking about the SEALs that, walk around with silenced weapons and can kill you. You don't want to, talking to a SEAL team commander and say, why are you boneheads building stuff out here on the beach? Why are you doing that? This is a picture from the 70s, California Coastal Records Project. If you're not familiar with that, you should be. You see this U-shaped building over here? There it is right there. That's the U-shaped building. So not only do they go out here and they build all of this stuff, but they come along and they make special trips to Scripps and they go, we really need to talk to you about how come our beach is so narrow. Well, they train on the beach, right? Every SEAL, no matter where they end up deployed, every SEAL, all the SEAL teams, including SEAL Team 6 that took out bin Laden, trains in Coronado. They are all training in Coronado at this particular base. So the beach is a critical part of their training. Now, the answer to that is, Mr. SEAL Commander, your beach is very wide. You see how wide it is? And this gets into a whole different matter that I haven't talked about at all. And that is the condition of this beach and the condition of Santa Monica Bay, for example. Those beaches are artificially wide. They weren't that way naturally. They were artificially wide because of nourishment. So this beach is in no way narrow. It's very wide, except that you've built on 3/4 of it. And so it just looks narrow. So this is the kind of thing that we have to consider going forward to basically do no more harm than we've already done. Okay, I'm getting there now. So this is the 5.5-foot scenario. We did some work for the LA region recently. This is that artificially wide beach at Santa Monica Bay due to construction of the airport, the Hyperion sewage treatment plant, the Marina Del Rey culminating in the late 60s when it was completed. So you look at pictures of this beach in the 1930s and there's literally waves breaking during storms into these front row houses, which were little, bungalows in the 30s, and now we're $5 million homes, but never mind. The beach in Venice, for example, or Santa Monica, people complain, and by the north jetty of Marina Del Rey, people complain because the beach is 1,000 feet wide and you burn your feet. It takes you half a day to get from the parking lot to the edge of the water. That will change. So this is that trajectory, the 5.5-foot by 2100 trajectory. So the shoreline in 2030, 2050, and 2100 is on there. So Santa Monica is in good shape, as most of the wide beaches in that part of LA are. But you go up to Malibu and it's an entirely different matter. And so by 2100, there's going to be very serious undermining of the highway, undermining of a lot of development, probably complete loss of the beach. Eventually, there's a point of sea level rise rate where sea level goes up too fast for the beaches to keep up. There's not enough sand in the system that can move fast enough, and/or in the offshore system, and/or the cliffs are too hard, they're too resistant to erosion to be able to erode fast enough to provide enough sand to maintain a sandy beach. And this is known going back again to that paleo, the sea level rise over the last 20,000 years. You can see cliffs and wave-cut terraces out. There's a 10-fathom terrace, 60-foot depth, where the archaeological record shows you during very rapid rise in sea level, there is no beach because you don't see the terrace built, because it rises too fast for that wave-cut terrace to build and be able to accumulate sand. And that's probably the future of our coast.
2 lots, 3 lots deep.
So 2100, yeah, it's deep and it's in the cliffs too. So my dear wife and I had a granddaughter about 3 weeks ago, and I thought about this. So 2100, Jerry and I, well, Jerry might live to 2100, but I certainly won't. But our granddaughter probably will. So she was born, she'll be 87 in 2100. So I think about this. My grandparents were all born in the 1880s and 1890s. So that's the 1800s, 1900s, 2000s, and my granddaughter will span, so those 4 generations will span 4 centuries, 2100. And this is the one thing I regret. I love being old. I really do. I have all the money I need, and I know a lot more than I did when I was a punk. But the one thing I regret is I'm not going to see the worst of this hit the fan. I'm not going to live to 2048, 2060, 2070 when all of this stuff is actually going to happen. Yes?
I mean, maybe this is controversial, but, and we're talking about Southern California coast where pretty much if you live on the water, you are wealthy, so we're not talking about islands and other parts of the world. But isn't this kind of great in that we're undeveloping, like the Angeles National Forest used to be resorts and the fires just destroyed it, and now we have beautiful public land. And wouldn't it be great if the Malibu looked like Big Sur and there wasn't a highway on it?
That's one way to look at it, but you need to, well, I mean, I think Jerry can answer that question, and it has to do with what the economic value and the, where all these people are going to live, and the economic disruption that is in store if these sea level, especially sea level, but not just sea level, but everything else, species extinctions, mass extinctions, food shortages, water shortages, and the disruption that that's going to cause. So yeah, in some sense, if you want to go back to nature, but the cost to humans. So this, I think what you're raising is, indirectly has to do with the discussion that was very vivid in the 70s, but has all gone quiet, and that's population. And it went quiet. There was a thing in the paper or somewhere, I saw something the other day about, what's his name, the population bomb, Ehrlich, who's gone very quiet, because any discussion of population growth, immigration, all of this kind of thing automatically makes you a racist. Discussion of population and population growth from different sources, birth rates, immigration, always ends up, or at least lately ends up, in basically a coloring. It gets colored with a racial tinge. And so everybody stays away from discussing it. But the fundamental problem underneath all of this is there's just too damn many people. And that, it's not a racist thing, that's just a fact. Like Jerry said, and I was going to get into this in the very end, but I think we might be there. So let's agree that the goal here is to limit the worst climate change damages. So what are we going to do? CO2 sources. China has now overtaken the United States as the largest emitter of CO2. But if you look at the per capita, and especially the cumulative per capita greenhouse gas contributions, the United States is just overwhelmingly responsible for the majority. What are we going to do in the future? Well, these are some of the scenarios. And these numbers now refer to the radiative imbalance. So remember, we're about a little bit less than a watt per square meter. So the lowest of these trajectories down here, so this is cumulative CO2 versus temperature. Here's the 2-degree Paris. We're already at 1 degree. Here's the 2-degree Paris Accord. They're talking about radiative imbalances with business as usual in this 2100 trajectory of 8.5 watts per square meter, right? Up from this little bit less than a watt that we're at now. So, if we go anywhere into this range of 3, 4, 5 degrees, first of all, the short-term consequences will be drastic, but those consequences will continue to build for hundreds of years, maybe 500 or 800 years. So you think about the history of places like New York that were founded in the 1600s. They're barely 400 years old. Right? So you think about the future where all of that is flooded under lots of water and erosion and damages and flooding that occurs during these high tide episodes. I mean, you're talking about massive human disruption that is on an unprecedented scale. So, these people have had to move before during the last ice age when sea level rose. In Europe, it's well documented, but they had a place to move to. Where are we going to move? If we move south, the Mexicans will build a wall. Canadians probably would too. So I'm not going to dwell on this, but these are the kind of the reduction that we need. So currently CO2 is increasing at 3% a year. So here's one. So here's the idea is to peak, this one, the blue one, by a guy named Jim Hansen that you should become familiar with if you're interested in this stuff. The idea here is that CO2 peaks at about 425, right? We're already at 400 right here. Peaks at 425 around 2020 or so, and then starts to decrease because we decrease the input by 5% a year. Well, that means an 8% per year reduction because it's increasing by 3% a year. I mean, it's physically impossible, economically impossible to do, especially under current political conditions. So here's another way to look at this same thing, gigatons of CO2 and how we might have to reduce it in order to get to radiative imbalance, within the 21st century. So what can you do? Well, engage and speak out, and that includes scientists that are very reticent to speak out about controversial subjects for various reasons, one including the scientific methods. We don't like to talk about stuff that we're not certain about, reasonably certain about. Promote public recognition and acknowledgement. That's what we're trying to do here. Vote. Sometimes voting doesn't work, so then you have to demonstrate. Write and call elected officials. You know, well, sometimes the Russians vote for you. What are you going to do? You know, editorials. I've written editorials. Others, you join lobbies like the. I'm not promoting this. I'm just using it as an example. The Citizens Climate Lobby. They seem to have a sensible political agenda. For example, having a group in the House of Representatives, not by majority party, but equal numbers of Republicans and Democrats. So they'll find a Republican and then they have to find a Democrat. I think there's 20 of them now. Well, it's a start, right? Economic and legal actions, taxes, cap and trade, carbon fee and rebate. I'm not going to go into all this because I'm not an expert in it, but it's just stuff I've heard, and Jerry can talk more. Technology. I don't think there's any way to get to where we need to be energy-wise, making it cheaper without some kind of nuclear option. And I don't mean that figuratively, I mean literally, nuclear, some kind of nuclear power that's safe and not, not going to kill us in some other way. Then there's very controversial ideas about cloud seeding and aerosols and stuff, chemicals in the atmosphere to cut down on the radiation from the sun. Very, again, complex system. You start mucking with it in a little ways and you might have very big negative consequences. So finally to the beer, I've already said some of the philosophy of this. So this is on the Ross ice shelf where we installed 32 seismometers 2.5 years ago. This is where it really helps to be German, even when you're drinking crappy Dutch beer. It's still damn cold in Antarctica, right? This is the Ross ice shelf. It holds back half of the West Antarctic ice sheet. And the idea was to go out there and, with this guy, Peter Bromirski, this squirt in the middle, who's one of the rock star scientists in the world now in this business, the intersection of seismology, climate science, and coastal processes. He got this National Science Foundation grant that took us all to Antarctica to install these seismometers for 2 years to try to sort out the mechanical properties while this thing is still in shape. So this is, the Ross ice shelf is flat. It's very cold. It's about 20 degrees below zero in that picture. It's about the size of France, right? And it floats on the Ross Sea, and it holds back. It's about 800 meters thick at the root and 200, 600 feet thick or so at the edge, where it's floating and pieces break off once in a while and float off into the Pacific. And the idea here was, like I said, to use seismometers in the same way that they're used on land to find where the fractures are and what the mechanical strength and properties are of this thing as it begins to melt from below, because the water's warming, the ocean water circulating underneath it is melting. The seismic signals are actually generated by waves that originate both in the North and in the South Pacific. So North Pacific, very long waves, propagate halfway around the world and penetrate underneath the ice shelf and flex it on a continuous basis. And so that's what we've installed there and measured. They pulled the instruments after 2 years a couple of months ago. So let's see, I guess I'll leave you with that. Thank you very much for your attention. Yeah, I got all night. So.
All right, go ahead, ask it.
Go ahead.
We are confronted with people who want to say that it's not, that it's warming, but it's not due to human actions or what all science says.
I had that note, and one of my slides had that note with the Chinese hoaxsters. Yeah.
Is there, if you were to say in a short conversation, 1 or 2, 2-minute response to that without getting into an argument?
20-second, yeah.
And just saying you're stupid. What would you say to them?
Yeah, well,
You
that's,
run into this now in,
yeah, I know.
the world.
That's why I'm so bad about this, because that's my first reaction. You dumb shit. No, seriously. I think one way to, well, you know, one effective way that's been found, I can't remember who came up with it, but the idea of the creation. Right, you're messing up God's creation. You know that.
The response to that would be.
Well, but that's
God will
effective.
the answer to that is God will take care of us.
Yeah, well.
We're needed to, so no worries.
Yeah. Well, okay, that could be.
I would not use
Yeah,
that
that could be, and I think so. The short answer to many people that you know that are convinced that this is either a hoax or some kind of a conspiracy or fake science or something. My feeling is that no matter what you say, it's not going to matter. It's not going to change your mind. Okay, so with some people, maybe the approach of, okay, maybe it's not true. Maybe there's uncertainty about the degree, the timing. What if it is true? What can we do that is good anyway? You know, like coal. I mean, this thing with coal. You know, coal has so many bad environmental and health effects that alone, you know, should be, and then now economic, right? There's no, the economy of coal is, you know, is nowhere near the economy of gas, right, to generate power, right? It's much cheaper to do it with gas than it is with coal. So, so some things like that should, you know, should just be justifiable on a purely economic basis, or a health basis, or an environmental basis other than the warming part. Maybe Jerry has a better answer, but
No,
I'm as baffled as you are.
Let's take one more, and then I want to make a few closing comments. Go ahead.
This past year, we had the high tide, peak tide, and the water edge came up towards the walls and Belmont shores of the lagoon. Now, the worst scenario, wouldn't that flood all of Belmont shores in the downtown area?
Well, yeah, if it's high enough, it certainly will. But I took that slide out because I knew I was going to talk too long. I have the peak high tide projections, the monthly peak high tide projections for the next 100 years. And if you look at those, there are these 4.5 and 18 or 19-year cycles in the tide. So the winter of 2015-16, the past winter, we were actually in the low. So those were the lowest high tides of you know, the next 4.5 and the next 9 years. So in 2021, you're going to want to go out and look at the high tides because they'll be, I think, a foot or two higher. The high tides will be a foot or two higher than they were this past winter. So if you think you had a problem this past winter, just wait. Yeah. So look at the tide tables, you know, and try to find that. Next time I come, I'll bring that with me.
So I just want to add a few things. There is a great deal of uncertainty in the rate at which sea level is going to rise in the future, but I think all the more recent data suggests the probability is greater that it will be at the higher end rather than at the lower end. I think Jim Hansen is probably too high, but it's certainly the likelihood by 2100 that it's going to be a meter or more, 3, 5, 6 feet, I think the probability is fairly high. And I think one of the points that Ron made that I wanted you to be sure you caught was when he said some of these changes are baked in. What that means really is that if we eliminated all greenhouse gas emissions tomorrow, all of them, which we obviously cannot, the Earth would continue to warm for several decades, sea level would rise for decades, maybe centuries, and so we are going to live in a warmer world with a higher stand of sea level. The two areas, population, that is it's very difficult to talk about. We're doing something right now, again, on population. Most of the population growth will come in the developing world, virtually all of it. Most of the developed countries have stabilized or are even reducing their populations. The replacement rate is 2.1 children per couple. The reason you add the 0.1 is because some children die in childbirth. But in the United States, we're below that. Most of Europe is below that. But in some developing countries, the growth rate, the reproductive rate is 5 and 6 children per couple. And probably the biggest impediment is the lack of the opportunity for young girls and young women to get an education. And that we have to really turn that around. You stabilize population. This has been shown in Latin America. And you also then benefit from 50% of the population who have a lot of intelligence and creativity and innovation to contribute to what we do. So we need to work on that. On the energy, wind and solar, everybody's all psyched about these. They are renewable, but are they green? They are both low energy density sources of energy. That means you get small amounts of energy in large areas that they take. Wind farms, solar farms. I think we have to have some nuclear in the mix. I think California is making a mistake by closing one and scheduling the second one to be closed. We got 20% of our energy from those two plants. And there are better designs now with nuclear plants that are being installed around the world. But the U.S. as a whole gets 20% of its energy from nuclear, and we're beginning to phase most of that out. And when I say they're renewable, but they're not green, the biggest threat to nature, to wildlife, to biodiversity, is habitat degradation, fragmentation, and destruction. So now you take these big areas of nature and you build a wind farm. And every single windmill needs an access road so a pickup can get down there to service that windmill. And if you look at what they do to birds, and also, we really need to think seriously about that. And I would agree with Ron, geoengineering is not the solution. It could reduce the rate of solar insolation. We know that after major volcanic eruptions, Earth has cooled because the small aerosols, the sulfates that are put into the atmosphere, reflect a lot of the incoming sun. And there are proposals to inject aerosols and small particles into the upper atmosphere. A lot of unintended consequences are possible. We don't know what it would do. We do know that it wouldn't have any benefit to ocean acidification and what all the threats to the ocean. We may get desperate enough that at some point, someone will do that kind of a geoengineering experiment. So I think that population and agriculture are really key, because if you look forward, all the predictions are that by the end of this century, our food production, remember I said by 2050 we need 70% more. All the predictions are that because of climate change, we will have a net loss of primary production, crop production on the earth of 15 to 20%. There are winners, because if you warm, you extend the growing season. When you have more CO2 up to a point, you increase plant life. So some high latitude areas benefit, but over the entire world, we lose. So these are all big, complex and complicated and complex issues that fall into that category of wicked problems. Wicked problems are those that cross disciplinary boundaries. You cannot solve a wicked problem. There's no silver bullet. But if you formulate them properly, you usually can manage a wicked problem to keep it within bounds. Healthcare is another wicked problem. It's going to be interesting to see what we do with healthcare. So I think it's time. Next week, we have Peter Kariva. Peter is the director of the Institute for the Environment and Sustainability at UCLA. And Peter will be here to talk with us. We look forward to having you all back. How about one more round of applause for tonight's speaker?
That was fun.